Today, I am discussing the strength duration curve. This concept is nearly 120-year-old. That means it started in 1901, and the second postulation was given in 1907. And since then, there was always a thinking for finding the excitability for a excitable membrane. Here I have placed the two scientists who have given the concept and the basis for the strength duration curve. One, Dr. Weiss, a German neurophysiology or a neurologist, and with a lot of physics and mathematics background. And he gave this equation, what is known as a Weiss equation. In this, Q is equal to B times D plus C, or Q is equal to I times D. Q is the charges, as we see the charges across the membrane, transfer of charges across the membrane is equal to B is the Rho base strength, voltage, D is the duration of the pulse, and the C is the chronoxy. Then he simplified it to the Q is equal to the intensity, that is the voltage, and the duration. That is the basis for strength duration curve. Then in 1907, this French neurologist, he gave a understanding for this strength duration curve, that is Lepq. The Lepq's equation is I is the current is equal to B multiplied by 1 plus C by D. B is the Rho base, C is the chronoxy, D is the duration. Now, the concept generated by Weiss was linear, and this was rather different, giving a sort of a C-shaped curve. That is what they are. I will not go into the detail of the character of the mathematical these things and their details. You can read about it. And it is nice to remember Dr. Weiss and Dr. Lepq on this day, maybe 120 years even after, we are still trying to use this particular strength duration curve. What is strength duration curve and its importance? That's the first question emerges to anyone. It is the relationship between the voltage or the strength or the current and the duration through which it is passed to produce a response in an excitable membrane. This excitable membrane may be nerve, muscle, or whatever. And this is the relation. And this relation indicates the excitability status of the membrane. Whether it is easily excitable or less easily excitable or is non-excitable. It's a sort of a qualitative data. And it is an important tool, or it's a tool which helps us to know the extent of injury in case of a nerve injury or extent of degeneration in case of a degeneration. As happens in case of a diabetic neuropathy or a neuropathy due to some other diseases, the B12 deficiency, or so on and so forth. And also, it will be a tool to assess the recovery after treatment protocol, after an injury or after treatment, and how the nerve is recovering or how the particular excitable membrane is recovering. So it has an importance to know about that. Thus, having understood the importance of this strength duration curve, we move on to how it is determined. To understand how it is determined, we should first understand the stimulus and its parameters. An electrical stimulus usually nowadays is a square wave pulse or rectangular pulse is used. There are a number of electrical stimuli available, exponential pulse or abrupt DC current or whatever. The current standard method is to get the rectangular pulse like this, where this square wave pulse has the height. Height indicates the strength or the voltage or the current. And duration, because it abruptly, because this is the point where the square wave begins, abruptly there is a change in the potential difference or the current coming up abruptly, then it stays there for a period of time. That is the duration or width of this rectangle. So you can just see this, the height indicates the intensity and the width indicates the duration. Using this, the strength duration curve is constructed. Now, looking back here, the relation between the strength and duration is established by plotting the graph with various duration by varying the intensity, starting with a very small duration with increasing durations in a logarithmic scale, and seeing the responses occurring, a threshold response occurring by increasing the voltage. So that is how they're constructed. It is here maybe to impress upon you that stimulus of a very small duration, this very small duration, maybe 0.001 millisecond or 0.0001 millisecond duration, and even if you give a very large intensity, maybe 200 volts, 1000 volts, it may not be able to evoke a response. So that means duration should be adequate. The second, on the other contrary also, even if a large duration is used, maybe 100 milliseconds or 1000 milliseconds, but a very small intensity, it may not also be able to excite. That we would see in the strength duration graph. Having understood the electrical stimulus, it's a rectangular or a square wave pulse. It has a strength, that is the height, and it has a width, that is the duration. Usually duration is in milliseconds, the strength is in voltage. Then the threshold stimulus can be achieved by varying either the height or the voltage, or by altering the duration or increasing the duration, or both. You can use both the combinations. Having understood about the electrical stimulus, now see what happens to the excitable membrane in response to an electrical stimulus. Now, when we stimulate the excitable membrane, the membrane gets depolarized. And if this depolarization reaches to a critical level, that would produce a response. That we call it as a threshold. This process of depolarization involves transfer of charges. And this transfer of charges, when reached to a critical stage, that would produce if the number of charges accumulated, the positive charges accumulated inside the membrane, that would excite, and that would produce a changes in the membrane property, and that would produce an excite potential or a response. And this is called a response or a threshold stimulus. Now, the transfer of charges is proportional to the voltage or current applied, and also proportional to the time through which this voltage is maintained. If you are going back here, this is the voltage, and the time through which the voltage is maintained, that's the duration. So now, then that T is also involved. So that means transfer charge is equal to the strength times the time duration. That is the number of charges that indicates the strength of the transfer of charges or charges produced. However, in a biological membrane, like the excitable membrane, either a nerve or a muscle or a heart or wherever, what happens? It's not a static membrane, it is a dynamic membrane. If the charges are transferred across the membrane, there is what is called a leaky current. Some of the charges move out because if they are more, they move out. The greater time they are allowed, their movement is faster or greater. So that means net transfer of charges is equal to the voltage times the time, or voltage into the duration or time, and subtracting the leakage of charges resulting because of the duration of application. So now if the net charges transferred reach a threshold level, then that would produce a response. That's the basis of this. Then move on to this example here. I have given you a very simple arbitrary example or imaginary example. Suppose the membrane requires a minimum of 100 charges to evoke a response. And imagine that leaky current is variable. It's not 5 per unit time. It is 0.1 to variable per unit time. So that I will show you. The variable, I will use the word variable. You forget about this writing. So then the net transfer of charges, net transfer of charges is equal to V into T minus the leaky current. Now let us imagine if the charges transferred are greater than 100, then it would excite. That's a threshold or the threshold charges required for the membrane to be excited. Now, if let us assume here, if the voltage is 100, the charges per unit time it transfer is 1 unit. So 100 into 1 is 100 charges. 100 charges. Now, if in a given voltage it gives 100, that means I am telling 100 volts, it gives the 100 charges. 100 volt gives the 100 charge per volt 1 charge. Let us take it in that space. So 100 into 1 is 100 charges, and the leaky current, when the unit of time is small, leaky current is negligible. It is almost equal to 0. So that is why I have put 0 here. The total is 100, and this is 100 will excite the membrane. Then second instance in which I have a 50 volt, that means 50 charges are deposited. Time duration is 2 units, and 50 into 2 is 100 minus 2 times the leaky current. Leaky current is again with this time is negligible. So again it comes to 100. This will excite the membrane. Now, if again I will take an example of 25 volts where 25 charges, but the duration is 4. So that means there will be 100 charges. So what indicates the voltage and the time, they can be in combination used to produce the number or to produce the number of add the number of charges in a given environment. So you can have the multiples of the same to produce 100 as a unit charge per threshold. Now what happens? 25 into 4 is 100, and again the negligible leaking current. This is again 100. This would excite. Now what happened in case of a 20 into 5? The leaky current is 0.1, and it is 5 times the 0.1, so it would produce 99.5. Here I am drawing a line because it is much below the critical level of 100 charges, and this 100 charges is not reaching the threshold. It will not excite. Similarly, if I am reducing the 10 volt and I am increasing the duration, there are 100 charges, but the leaky current is increasing because the duration you have allowed is more, the more leaky current. And in that, because if you can see that leaky current increases exponentially with the time. So that means I'm just making an logarithmic scale. So that means it increases 0.3. So the voltage is 97, which is much big, or it is below the 100 charges. So now it will not excite. Similarly, if I reduce the voltage further 20 times units, 20 units of the time, it is again 100. But here it has increased, the leaky current has increased to 0.3 to 0.7, and it will be 14. 100 minus 14 is 86. You can construct these things, but the one thing in the red letters and put in the box, they are sub-threshold responses. They are not producing a response. So this is the basis of what happens in case of a strength duration curve. Now, let us see how to determine the strength duration curve. What is the procedure to determine the strength duration curve? Usually, we start with a low duration pulse. You can just see this low duration pulse. Here it is 0.001 millisecond. And I keep on increasing the strength of stimulus. Increasing the strength of stimulus. Even if I increase 140 also, it is not going to produce any response. So that means it will not produce any response even if I go up to the infinite voltage. So this is the first, that means it is not producing a response. So then here I have increased the duration of the pulse by 10 times, though it does not look like 10 times. But you can see that the time scale, whatever it is, 10 times this duration. Then I took this 0.01 millisecond pulse. And when I took the 0.01 millisecond, I keep on increasing the voltage. And at a particular voltage, it produced a response. And this is the threshold response, or this is the point I noted, and this is around 120 here. So now this produced the response. I put the dot there. I noted the dot. Now I increased the strength of stimulation or the duration to 0.1 millisecond. And when I increase the 0.1 millisecond, again I repeated by increasing the voltage. When I increase the voltage, it could be excited by 60 volts. So I noted that time, or that point. So this point is noted and this point is noted. Subsequently, I increase the duration further. Here I'm going in a logarithmic scale, 0.001, 0.01, 0.1, 0.1. And when I increased, and I found out the voltage required maybe around 25 or 30. So I noted the stimulus. So then I subsequently increased the voltage to 10. So again, I determined the threshold voltage. So it again remained around 20 or 25. So almost 20. Now I stimulated further to 100 milliseconds. Again, it produced at the same voltage. So that means it's a beautiful C-shaped curve. When I join these points, or even using the fitting of the best fit curve, you have the beautiful C-shaped curve with the convexity towards the origin. And this C-shaped curve indicates it has parameters. So that means in this C-shaped curve, you can just see that in this point, no matter how big voltage you are giving, if the duration is small, it's not going to excite the membrane. Here, no matter how long you give a stimulus or how long is the duration of your stimulus, if it is not of a particular critical voltage, it will not produce a response. These are the two aspects, say, in this side of the curve and in this side of the curve. So now I've just increased about the duration in millisecond, voltage here. Q, the charge is equal to V into T. V indicates the charge is transferred. The net Q is equal to V into T minus leaky current. If it is greater than 100, it produces a response. Now, if V is 100, that means we are giving 100 charges by giving 100 volts. Then T is 1 unit, 100 into 1 minus I, as I have already given, this reaches 100, that excites. The second point, if it is 50, again 50 into 200, but again because of the negligible current negligible leaky current, so it will be 100. So 25 into 4, because of the negligible leaky current with this time period, it will be 100. Subsequently, as the leaky current is becoming a predominant, so it is not able to excite, though the charges you have transferred is 100. As for the equation V and T, the charges we have transferred is 100, but it is not able to because of the leaky current appearing in this component. In a mathematical model, it is possible that we can be able to stimulate. If I give 100 charges for an infinite time, it may be detecting, but not in a biological model. Now, moving on, what are the various components of the strength duration curve? Now, in the strength duration curve, first point we want to find out the Rho base. Rho base is the minimum voltage when it is passed for adequate time. That would be able to excite the membrane. Rho base is the voltage that excites the membrane if given adequate time. This is Rho base. That's the first component of the strength duration curve. That is in terms of the voltage. Then we have another term. When we take the 2 times the Rho base, this is 2 times the Rho base. When we have 2 times the Rho base, the time required to produce a response with the 2 times the Rho base is known as Chronoxy. The time required to produce a response with the 2 times the Rho base is Chronoxy. And this Chronoxy units are in milliseconds, time units. Now I have defined Chronoxy. We will see the Chronoxy there. You will see the Rho base here, and the 2 times the Rho base determines the time duration of this Chronoxy. Now, utilization time. Utilization time is the time, what I'd say the adequate time, that is the time that can be used to produce the Rho base response. That is the utilization time. These are the components of the strength duration curve, especially Chronoxy and Rho base. Now we have another question there. The Rho base or Chronoxy, which is a better indicator to indicate or talk about the muscle excitability? Rho base is the minimum voltage that is required by the membrane if applied for adequate time. That is the Rho base. This is Rho base here. And units are in volts or amperes, whatever you are using here, the strength. The Chronoxy is the duration or a time required to excite the membrane at 2 times the Rho base value. Here, 3 strength duration graphs. One is A, you can just see this blue line, this is a curve. And another is C, red line. Now, let us compare A and C. What is happening? Both of them have the same Rho base value. Okay, can you see that? This is the Rho base value for A as well as C. Now, if I were to see this Chronoxy for a blue line, so that means twice the Rho base value, this intercepts here in this, and this is the Chronoxy, and this is the Chronoxy for A. This is shorter, this is less. Now, in case of the red line, you can just see the red line. So the Chronoxy, if I want to calculate, twice the Rho base value intercepts this curve here. And this is the duration for the Chronoxy for C. So that means the A is easily excitable and C is less easily excitable. That means in the excitability range, it's more excitable, it is less excitable. That means it requires a greater strength or a greater voltage or greater duration. Now, I have another curve here, B. In this curve, both the Rho base is shifted up and the Chronoxy is also accordingly has been changed. So that means it is a shifting of the curve to the right. You can just see that this is shifting of the curve to the right. And here I have shown such curves may happen in a different nerve groups. Maybe we have a B, C groups, A again, A alpha, A beta, A gamma, A delta. So, or after a nerve injury, this is shifted to the the rightwards. As they move on, so more injury, they may come here. I will show you some of those graphs. Now, so now with this, what we can infer or what we can confirm, the chronoxy is the better indicator to assess the excitability of the excitable membrane. Now, you can just see that the chronoxy have an inverse relation with the excitability. Lower value indicates the greater excitability. Here you can just see this is a motor nerve, the chronoxy C is equal to 0.01 millisecond. In all these cases, the Rho base is same. And it's a sensory nerve where chronoxy is 0.1 millisecond. This is the pain carrying fibers, C fibers. The chronoxy is 1 millisecond. Just going further. The cardiac muscle, chronoxy is 2 milliseconds. Skeletal muscle, because these are nerves and this is a muscle. So muscle, this is 10 milliseconds. So that means the excitability is indicated by the chronoxy, and the lower the value, the greater the excitability. That is, it has an inverse relation. So thus it discriminates different types of nerve fibers. Suppose if I am taking out the nerve fiber and trying to see the chronoxy, and suddenly I can say that yes, it fits into the second C fiber pattern. 1 millisecond if I know the chronoxy. So further, the chronoxy indicates the nerve injury or prognosis in a given. So maybe when a nerve injured, this is shifted towards the rightwards. Maybe here I will take an example here. This is an example of this strength duration curve in a patient with a motor nerve injury, showing its regeneration after resuturing operation. Now, this is the point, this is the standard normal strength duration curve. Then this is after the injury, that is before operation. Before operation. Operation is a resuturing. The nerves are put them together, or they are brought nearer in approximation, and then they were sutured. So now, this is, see for example, this is strength duration curve here, it is shifted to the right. So now, after operation, what happened? So this strength duration curve is almost near the same or slightly shifted rightwards. 2 weeks later, it moved to the left of this before. This is before operation, that is after injury. Then 10 weeks after operation, it's 8 weeks after operation, it's 10 weeks after operation. You can just see that it has shifted leftwards. So that means it is indicating that the nerve is recovering and regenerating. 16 weeks, it has moved further to the left. This is normal towards the normal. 25 weeks, it has moved to the near the normal values. Maybe if you have followed it further, it may come nearer, may not reach the original level. So this is the point where you can see or you can identify whether the patient is recovering or not. What happened to the patient after injury, and this is the importance of the strength duration curve. Now, I just want to summarize the points here. The importance of strength duration curve is to assess the excitability of a membrane. That's point number 1. And in that, chronoxy is a better parameter to express the threshold value, not the Rho base, because I have mentioned Rho base may be same, but chronoxy is different. The strength duration curve provides a qualitative assessment of the damage and functionality of the nerve or a muscle after injury. Thus, it is diagnostic qualitatively. It may not tell the extent to which we cannot quantify exactly, but qualitatively, yes, it will say that there is a damage. Then, strength duration curve also gives a prognostic indications that whether it is improving or not improving. As I have shown in my earlier graph, here in this graph, what it is shifting towards the leftwards, that indicates the recovery of. Suppose if it does not recover, so that means whatever the procedure you have adopted is not successful. That is the importance of the strength relation curve. Now, in this, the reference books, the Samson writes the applied physiology is the one which gives a little bit more information about strength relation curve, and also the neuroscience principles of neuroscience by Kendall. And we have in Guyton and Genong, we have a references not giving in a detail of account of the strength relation curve. Okay, that is, these are the books I referred. In addition, I have my own books, that is Mount Castle and Rose and Fulton, which I am not able to bother you with those books. Okay, I would give the assignment just to work on to the assignments. Write briefly on, forget about this, write briefly on Chronoxy, base, utilization time, strength duration curve, and its importance. And just fill in the blanks just to test your after nerve injury, strength nerve duration curve shifts to dash, dash, dash. The strength duration curves of B fibers in a peripheral nerve is to the dash, dash of C fibers and to the dash, dash of A fibers. You complete these things and test yourself whether you have got the information I'm trying to share with. Thank you. In the next class, I will talk about the resting membrane potential. That's another important topic which we need to work on. So now, thank you. Please subscribe to the channel. Leave comments in the box. Mention any topics you or questions you want I should discuss. I'm more than happy to do that. Thank you.